Yes, cool. So we want to find the highest, the lowest, the leftmost, and the rightmost points for parametric functions. And should be pretty easy, really, because a highest or a lowest point should only occur if the rate of change for y is equal to 0 or if it's undefined. And a left or rightmost point should only occur if the rate of change of x is 0 or undefined. So all we need to do is figure out what when dy dt is 0 and when dx dt equals 0 and see what we've got going on there. And there's a little bit more to it than that, but we're going to start with that. So does that make sense to everybody to start with?
Yeah.
All right, so we're going to do highest and lowest first. So we want to find dy dt. So what's dy dt?
T squared minus 4t minus 12.
T squared minus 4t minus 12. Clearly never undefined. So when does it equal 0? Well, that'd be t minus 6 and t plus 2. Yeah. So t equals 6 and t equals -2. Everybody agree with that? Hopefully.
Yeah.
All right. So something between -2 and 6 would be 0. If you plug that in, you're going to get a negative. And I guess now we can put in that function should be decreasing. And if we plug in a t value more than 6, then what should be happening? Should be getting a positive, so it should be increasing. And if we plug in something less than -2, like -1,000,000, we should get a negative and a negative, which should give us a positive, which means we should be increasing. So we'll deal with what all that means in just a second here. But first I want to do the leftmost and the rightmost. So if we're going to do left and right, we're going to need dx dt. And what's dx dt?
3t squared minus 12.
And if we divide out 3, or factor out 3, and solve that, we end up with t equals plus or minus 2. So -2 and 2. And if we plug in something in between, like 0, we get a negative, which tells us that the x values are decreasing, so it's moving to the left. And if we plug in something greater than 2, like 1,000, this is positive. And something negative, like negative, something large negative, like -1,000, then this becomes a positive also. And so real quickly, I want to pull this up in Desmos just so we can take a quick look at it. All right, we had t cubed minus 12t, right? And what was the second one? It was t cubed over 3, or third t cubed, right? Minus 2t squared minus 12t. Was it +1 or -1, or what was it?
+1.
+1? Okay. So we're going to start not at 0, but we're going to start at like -100. And we're going to go to, what was the first highest or lowest point that we might have had? Or first, it was -2, right? It was the highest. I think that was supposed to be a highest point. Is that right?
Yeah.
Yeah. It is also supposed to be a rightmost point. So if we go from -100 to -2, it's just looking like this. And if we go a little bit beyond that, let's say to 0, we can see that it stopped there and it started decreasing and moving back to the left. And then we ended up at 2 with a leftmost point. And if we go a little bit beyond that, we can see, yep, started curving back the other direction, right? But still going down. And then the next point we had was at, what was it, at 6? So at 6, I have to zoom that out a little there. At 6, it's going to hit a minimum there. And if we continue past that, like to, I don't know, 100, let's say, it increases. And if we keep zooming out, we can see that eventually, oh, that's not what I meant to do. Eventually, it's going to go back above that point. So we don't have a highest point because this function continues increasing to infinity. And we don't have a lowest point because it keeps decreasing down to negative infinity. And it doesn't have a leftmost or a rightmost overall, like an absolute left or rightmost point. But it does have local leftmost and local rightmost points, and it has local maxes and local mins. Okay. And so we would be able to tell that it doesn't have any absolutes because we know that these don't have any asymptotes. And so this is increasing forever and decreasing forever and moving to the right forever here. And this is from the negative moving to the right, which means if I was going to negative infinity, it's going to the left forever. The values are getting smaller. Does that make sense? So we have a local max at at t equals -2. And we have a local min at t equals 6. And we have a local rightmost at t equals -2. And we have a local leftmost at t equals 2. Good or no?
How do you know it's local and not like absolute again? Could you explain that?
Yeah, so it's not a local max or a local min because this is increasing once we go past t equals 6. And we know that these y values are increasing without bound right there. I mean, they're just getting larger and larger and larger the larger numbers I put in. I'm definitely going to get above whatever I plugged in at -2. Just because it's a polynomial function, right? I mean, polynomial function is going to look like this, right? If it's cubic. So
Yeah.
it's going to decrease forever and increase forever. So we don't have an absolute max here because it increases forever, and it don't have an absolute min because this way it's going down as it goes to the left forever. Does that make sense for the max and min?
I see.
Yeah, and same basic concept here. This function, the x values are increasing, but they're also, they're getting smaller as the t values become larger negatives. The x values are getting to be larger negatives also. So this is getting very, 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 very large negative x values over here. And then it hits a local rightmost point and then a local leftmost point, and then the x values get very, 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 very large as the t values get very large also. So same concept, because there are no restrictions on what x or y does as x or y approaches infinity and negative.
Okay, thank you so much.
Yeah. All right, let's take a look at this one. Now this one's a little different because, I'm sorry, anybody have any other questions on that one before we move on? All right, so let's take a look at the next one. We have x of t is cosine 3t and y of t is t squared minus t minus 1. Still looking for our highest, lowest, left, and rightmost points. But this time we are given a restriction on it that t is between 0 and 2 pi. So now we're probably going to have some absolute points here as well. So first off, we need to find dy dt, we need to find dx dt. So what's dy dt? That's right, it's 2t minus 1. And when does that equal 0? At t equals 1/2. Is that on our interval from 0 to 2 pi?
Indeed.
Wonderful. All right. And then let's find dx dt. Dx dt is the derivative of cosine 3t. So that ought to be what? Negative 3 sine 3t. We want to know when does that equal 0? Well, that equals 0 whenever the sine of 3t equals 0. And that'll happen whenever that angle, when does sine equal 0? Well, at 0 and at pi, right? And then at 2 pi, and then at 3 pi, and then at 4 pi, and at 6 pi. So 0 plus every pi n, or t is equal to just pi n over 3. Good or no?
Great.
All right, so on our interval from 0 to 2 pi, that'll be 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, 5 pi over 3, and 2 pi. Quite a few values there this time. It would appear. Start with the easy one over here. T equals 1/2 for our highest and lowest. Plug in something between 0 and 1/2, like a quarter. We get a negative, right? Plug in something between 1/2 and 2 pi, like 1, and we get a positive. So our function is decreasing, and then our function is increasing. So we should have a local minimum at 1/2, and it looks like that should also be an absolute minimum at 1/2. You guys agree with that?
I do.
Okay. So we'll say a local and absolute min at t equals 1/2. We'll find the points this time. I know we didn't on the first one, but we'll find them this time. And now we need 0, we need 2 pi, pi over 3, 2 pi over 3, pi, 4 pi over 3, and 5 pi over 3. Good or no? All right, I'll assume that's good. So something between 0 and pi over 3 will be pi over 6, let's say. If I plug in pi over 6, that's going to be the sine of 3 pi over 6 or the sine of pi over 2. What's the sine of pi over 2?
1.
1, and multiplied by a negative, then we have a negative inside of here. What about something between pi over 3 and 2 pi over 3? That'd be like pi over 2. If I plug in pi over 2, this becomes 3 pi over 2. The sine of 3 pi over 2 is negative, times a negative is a positive. Something between 2 pi over 3 and pi, like 5 pi over 6. That's going to become 5 pi over 2. That's just going to become another pi over 2, which is going to make this negative. And you'll probably note that this is just going to alternate back and forth here every time. So if I go between pi and 4 pi over 3, that's going to be 7 pi over 6, which will give us 7 pi over 2 when we multiply by 3, which is the same as 3 pi over 2, which is negative, times another negative is a positive. And same thing here, going to go negative and then go positive. Everybody good there or no? Yeah or no?
Yes.
All right. So then we just need to figure out what's going on at each of these values. So what's the cosine of 0? What is the x value at 0?
1.
1. What about the cosine of 3 pi over 3? That's the cosine of pi, which is
-1.
-1. And then if we go with 2 pi over 3 times 3, that's going to just be the cosine of 2 pi, which will be 1. And then we're going to end up with that cosine of 3 pi. That's going to be -1. This one's going to be 1, and then another -1. Everybody agree that that's what the pattern is going to look like?
Yeah.
All right. So our rightmost points are what?
Oh wait, you have to know the y values too, right?
I'm just going to go with our rightmost x values are x equals 1, and the leftmost are x equals -1. Yeah, and we could go and plug each of those in there and evaluate to see what the actual coordinates of the y value are, but I'm not going to make you guys do that. And then over here, we had an absolute and local minimum at t equals 1/2. And so if we want to find the actual y value there at t equals 1/2, that would be y equals what? 1/4 minus 1/2 is negative. 1/4 minus 1 ought to be -5/4 at t equals 1/2. Good or no? Cosine 3t, and what was it for t squared minus t minus 1? So if we go from 0 to 1/2, let's go from 0 to 0.2, we can see we're starting right here, and we're going this way. And if I go to 0 to t equals 1/2, we hit this local minimum, which ends up being an absolute minimum, like we said. So if we continue on to 1, it makes it all the way back to here. And if we put all the way in there 2 pi, we can see that we're hitting, that's our rightmost, then our leftmost, and then our rightmost, then our leftmost. And each time these oscillations are getting a little bit, expanding out a little bit, because each time we plug in that y value, it gets a little bit larger. Good or no?
Yeah, that makes sense.
Any questions, anyone on that?
If there's just like a whole load of sine values that would work for, or no, just values that would work for t, like for what you did for dx, is there any time you would expect us to find the absolute, like absolute maximum?
Yeah, definitely. And we should do that here on this one as well. So we need to find our absolute maximum here. Oops. So we need to find our absolute maximum here. And so since we know that our y values are, getting larger as it gets towards 0 and getting larger as it gets towards 2 pi, we can plug in y. I should just make the red color. We'll plug in t equals 0. That gives us a y value of -1, and we plug in 2 pi to get that that's 4 pi squared minus 2 pi minus 1. And clearly 4 pi squared minus 2 pi minus 1 is greater than -1, so this is our absolute max on that interval also. So yeah, we should do that. That's what you're asking, right? Whoever was just talking.
I meant for like dx, there's like a load of t values that would work for it. So you would want us to test all those to find the absolute max or minimum, correct?
Oh, for the x? Well, I mean, we did. We tested them right here. We got 1, -1, 1, -1, 1, -1. But they're not absolute max or min. They're just the absolute rightmost and leftmost. And they all come out either 1 or -1, though.
Well, like for this one, since it oscillates, like it would be easier. But like, say it would be like a bunch. Would you expect us to test them all?
Yeah, you got to test them and figure out which one is absolute. Yeah. Yeah. Any other questions on that? Oh, somebody sent something in the chat. Oh, yeah. I guess I answered your question, huh, Ryan? Looks like. Everybody good? Any other questions there?
Wait, can you, where'd you get the -5/4 again? You plugged in t equals 1/2, right?
Yeah, into the y. Y of 1/2 is, as long as I did that right, 1/4 minus 1/2 is -1/4 minus 1. Yep, -5/4.
Okay, got it. Thank you.
All right, why don't you guys do this one on your own? This one is not too bad, actually. This one's pretty easy. Note that it's open on the t equals 0 side because you can't plug in t equals 0 into natural log and get an actual value. So half open interval 0 to 10. And then this is our parametric. So see if you can find highest, lowest, leftmost, rightmost if they exist, absolute and local. Ready, go. All right, so first off, what's dy dt?
3e to the 3t.
3e to the 3t. And what's dx dt?
1/t.
1/t. Right. Okay. And when does 1/t equal 0, or when is it undefined?
Never on this interval.
Never on our interval, right? Never equals 0 ever, and it never is undefined on our interval. So it never undefined on 0 to 10. And what about dy dt? Does that ever equal 0?
Nope.
No, and it's also never undefined. Nice and easy. Right, so all we need to do then is figure out what's going on this interval between 0 and 10 to each of these. So here's 0 and here's 10. If I plug in some number between 0 and 10, or 10 for that matter, what do we get for our y value? We get a positive or a negative?
Positive.
Positive, okay, which means we're increasing, which means that if we're not approaching, we're approaching 0, but if we ever hit 0, we're never going to have a lowest point, but we will have a max at 10, right? We'll have a local and an absolute max at t equals 10. And what is that value? It should be e to the 30th power. And what about our dx dt? We should do the same thing. Between 0 and 10, plug in anything we want in there. What do we get, positive or negative?
Positive.
Positive, which means it's always moving to the right. Say that again. No? Okay. And so we have a rightmost at t equals 10, and it should be to the right at x of 10, which is the natural log of 10. So our rightmost point is an x value of natural log of 10. Our highest value is at e to the 30th. And since we don't ever actually hit 0 on either of those, we don't have a leftmost and we don't have a lowest point. Good or no?
Gorgeous.
I agree. Anybody have any questions or issues on leftmost, rightmost, highest, lowest on these parametrics? Nobody? Cool. All right. In that case.
Oh, I have a question.
Oh, okay.
For that very first problem, would we technically say there is no highest, lowest, leftmost, rightmost because it's local and it's not like absolute?
Right, we could only state that they're local, but there are no absolute max, min, rightmost, or leftmost absolute. Correct.
Okay, got it.
Yep. All right. L'Hopital's rule, which you should be familiar with, right? Yeah, hopefully. Yeah. So we know that if we have a limit that is 0 over 0 or infinity over infinity, we can use L'Hopital's rule to evaluate it. So L'Hopital's rule says take the derivative of the numerator, take the derivative of the denominator, and reevaluate that new limit. We can do that as many times as we need to get to a limit that doesn't come out to be indeterminate. So if you keep doing this and it keeps coming out indeterminate, you can just keep going through and doing it until it's no longer indeterminate. And you may at some point have to do a little bit of simplification in there. But this is L'Hopital's rule, and we're going to look at the basics of it when it's 0 over 0, infinity over infinity. Then we're going to look at a bunch of other indeterminate forms and how to put them into something that we can use this for, and just some other limits in general that we're going to use. So these two should be easy. First thing you should always do is what with your limits?
Plug it in.
Plug it in. And so if we plug in 2, we end up with 0 over 0, right? Which tells us we can use L'Hopital's rule. And they want you to write out that you're using L'Hopital's rule. They don't want you to write LH. They want you to actually fully write out L'Hopital's rule, which is stupid, but that's okay. So I'm not going to write it out every time. I'm just going to put an LH, but you guys should be writing it out every time. So this becomes the limit as x approaches 2 of the derivative of x squared minus 4, which is 2x, over the derivative of x minus 2, which is 1. Plug it in, you get 2 times 2, or 4. How else could we have done that one?
Could have factored it.
Could have factored. Exactly. Factored and canceled. All right. Let's look at the next one. What should we do first? Plug in the 0. Square root of 1 minus 1 over 0 is 0 over 0, indeterminate. One way we could do this is multiplying by a conjugate, right? But we're not going to do that. So you could also use a u substitution. Actually, that'd probably work better. I don't think multiplying by the conjugate would really work. It might. Yeah, it probably would not. Okay, so this is 0 over 0. So we can use L'Hopital's rule. What's the derivative of root 1 plus x minus 1?
1 over 2 times root 1 plus x.
Yep. And then all over 1. Now we can plug in our 0, which gives us just a half. Good or no? All right, what about this one? Plug in the 0, right? What does that give us? Gives us 0 over 0. So using L'Hopital's rule, this becomes a limit as x approaches 0 of the derivative of the top. Well, root 1 plus x is 1 over 2 root 1 plus x. The minus 1 is 0, and the minus x over 2 is minus a half, all over 2x. And if you plug in 0, you get a half minus a half, which is 0 over 0. So still indeterminate. So now what do we need to do? We need to use L'Hopital's rule again. And what's the derivative of 1 over 2 root 1 plus x? That's 1/2 of 1 plus x to the negative 1/2. So that should become what? Negative 1/4 times 1 plus x to the negative 3/2. All over 2. Everybody good with that or no?
Yeah, it looks good.
And that gives us negative 1/4 times 1 to the negative 3/2 all over 2, which is negative 1 over 8. Good or no? So we can apply the rule multiple times. If we still got 0 over 0, we could just apply it a third time if we needed to. This one's nice, right? It's really a pain if you have to do it without using L'Hopital's rule, but using L'Hopital's rule, since this is 0 over 0, this just becomes a limit as x approaches 0 of cosine x over 1. Should write that I'm using L'Hopital's rule, and that just gives us the cosine of 0 or 1. Right? Remember, that's one of the ones we need to have memorized. Yeah. Good or no? All right, what about this one? The limit as x approaches pi over 2 of secant over 1 plus tangent. So what happens if I plug in pi over 2 to secant x? That's the secant of pi over 2, right? Well, the secant of pi over 2 is the same as 1 over the cosine of pi over 2, which is what? What's the cosine of pi over 2?
0.
0, right? So I have 1 over 0. But really what I have is 1 over something that's very, 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 very close to 0, 1 over a very, very small number, which is going to go towards a very, very large number. So that's going to become an infinity. And then in the denominator, I've got 1 plus tangent of pi over 2. Well, that should be, what's the tangent of pi over 2? That's where we have an asymptote, right? Sine of pi over 2, which is 1 over cosine of pi over 2. So it's also infinity. So everybody agree that we have an indeterminate form there, infinity over infinity?
Yeah.
Good. So using L'Hopital's rule, this becomes the limit as x approaches pi over 2. Derivative of secant is secant x tangent x. Derivative of 1 plus tangent is secant squared x. And we could simplify by canceling out some secants, right? Before we try to evaluate. That'll just become tangent x over secant x. And what do you get if you plug the pi over 2 into that? What's the tangent of pi over 2? It's 1 over the cosine of pi over 2, or 1 over almost 0, so infinity. And same with the secant, right? Still infinity over infinity. So what should we do next?
Could we simplify again? Since tangent x over secant x would be the same as, unless I'm messing up, sine x.
It should be, yeah, it should be the same as sine x, and we do want to do that. If we try to use L'Hopital's rule again, we'd get secant squared over secant tangent. We just get the reciprocal of what we had before, and the secants would cancel, right? And we'd end up with secant over tangent instead of tangent over secant. And if we tried to do that again, we'd just flip back to tangent over secant and back to secant over tangent repeatedly. And so we got to find a way to simplify the trig, and what you said is exactly right. This is the same as the limit as x approaches pi over 2 of sine over cosine over 1 over cosine, which is just sine. And as x goes to pi over 2, sine x is just the sine of pi over 2, which is 1. Everybody okay with that? Perfect. All right. Why don't you guys do this one on your own real quick? Ready, go. Infinity of sine of 1 over x over 1 over x. Why would we do that?
Because now it's an f of x over g of x kind of thing.
And what is it? It's a 0 over a 0, is it? And since it's indeterminate, there's a couple different ways we can go about this one. Anybody see a good way to go about this one that doesn't actually require us to use L'Hopital's rule?
This is probably very wrong, but sine u over u is 1, right?
Say that again.
That property where, oh wait, no, x approaches infinity. Never mind, I'm done. I'm dumb, sorry.
You don't need to disparage yourself, but that would have to be a 0. But you're on the right track. This does look very much like that, right? Well, what if I just let u equal 1 over x? As x approaches infinity, what does u approach?
0.
0. So this would just become a limit as u approaches 0 of sine u over u, which is 1, like you just said. Or if we wanted to go through and use L'Hopital's rule, we could. This would then become a limit as x approaches infinity of the, let's see, sine of 1 over x would become cosine of 1 over x times the derivative of 1 over x, which is what? Negative 1 over x squared, right? And that would give us a negative 1 over x squared in the denominator also for the derivative of 1 over x, which would just give us a limit as x approaches infinity of the cosine of 1 over x if you simplify out and cancel out the negative 1 over x squareds. And if x goes towards infinity, 1 over x is 0, right? So this is just the cosine of 0, which is 1. So if you see the substitution, cool. If you don't see the substitution, then also fine, just use L'Hopital's rule. Good or no?
Why can't you use L'Hopital's rule on the original function?
Well, you don't have a quotient of 2 functions. It has to be written as a quotient of 2 functions.
Oh, okay.
So you can take the derivative of the top over the derivative of the bottom.
So
Which is why we
even
wrote
if-
this quotient here, so that we would have quotient of 2 functions. It was still that indeterminate form, which is why L'Hopital's rule works. Good or no? All right. Next indeterminate form, infinity minus infinity. So we've talked a little bit about this one. I don't know if we did it this year, but you might have last year. Remember I gave you guys something like e to the 7x plus 7e to the 4x minus 8e to the 3x minus 7e to the 2x plus e to the negative 4x. And we were looking at the limit as x approached infinity or something like that. Right, this came in infinity minus infinity to make it indeterminate. We did some factoring on that, but most of them don't turn out nicely like that. Most of them are more irritating like this. So if I have the limit as x approaches 1 of 1 over ln x, that's 1 over 0, which is infinity, minus 1 over 0, which is infinity, right? Because remember that those zeros are not actually zeros, they're just numbers very, very, very close to 0. So 1 divided by something very, very close to 0 is infinity. So this infinity minus infinity has to be dealt with. Any thoughts on how we'll deal with that?
Pick a common denominator first.
Common denominator. Good. Okay, so that's going to give us a limit as x approaches 1. And that's going to give us x minus 1 here, and then minus an ln x there, all over ln x times x minus 1. Good or no?
That's great.
Good. And now plug in your 1. What do you get? You get 1 minus 1, which is 0, minus the natural log of 1, which is still 0, over our denominator, which is natural log of 1, 0, times 1 minus 1, 0. Well, now what can we do since we have 0 over 0?
L'Hospitals.
That's right. And take the derivative of the numerator. What's the derivative of x minus 1 minus ln x? That'll be 1 minus 1 over x. And then in the denominator, we got natural log of x times the derivative of x minus 1. Right, so that's just 1. And then plus x minus 1 times the derivative of natural log of x, 1 over x. Good or no? All right, let's plug in our values and see what we get. We got 1 minus 1, bummer, that's 0. And then down in the denominator, we've got natural log of 1, which is 0, plus, what does this become? This becomes 0 times 1, 0. Bummer. What should we do? We end up with 0 over 0 again. What do you think we should do?
Do it again.
Sure, why not? The 1's going to cancel out this time, right? What about this negative 1 over x? That ought to just become 1 over x squared. And then our denominator, natural log x, should just be 1 over x. And if I were to distribute this through, x times 1 over x is what?
1.
1. So the derivative of 1 is 0. So I don't need to put that. And then minus 1 over x is going to give me plus 1 over x squared. Everybody agree with that as the derivative there? No? Yeah, maybe?
Yeah.
Great.
So plug in your 1. So now you got 1 over 1 over 1 over 1 plus 1 over 1. Or a half. Good or no?
Exquisite.
Wonderful. So infinity minus infinity. Generally, when you have infinity minus infinity, you're going to need to find some way to combine those things together to give yourself a common denominator so that you can use L'Hopital's rule. All right, we're going to stop there because we're not going to have enough time to get through any of the next ones, and they take a lot more time and explanation. So that will be it for today. Any questions?
Is there a good way to tell when doing a L'Hopital's rule will just give you the same thing over and over again, like indeterminate, or for this one you would know that it would actually work out if you kept doing it?
I mean, eventually, unless there is simplification of the actual thing inside the limit that needs to be done, it will eventually come out to some number. Or it'll come out to be undefined. It'll be like a 7 over 0 or something. Usually, there's not a lot of simplification required to make it work out unless it's trig functions. So if it's trig functions, for sure always look at simplification, but just in general, always try to simplify as much as you can just to make sure that terms don't cancel. But it should, like I said, unless it's trig functions that need simplified, it should within a couple times come out to be something that's no longer indeterminate.
Okay, thank you.
Any other questions?